Hello everyone and welcome back to this second lesson of this course, Data Science for Doctors. I hope you liked the first one, and so since we've got a lot to cover in this second lesson, I think we should better get started. Now, there are lots of concepts in statistics, and it would be really difficult to go through each and every one of those. But what I'll try to do in this second lesson is that I'll try to focus on those concepts which are really practical and which would be needed by you when you'll be doing your own analysis with your own data. So let's quickly have a look at the outline of what we are going to study. We'll start with understanding the data types and the variable types. We'll then go on to understand what are the central tendencies and how to understand the spread and confidence intervals of a given data set. We'll then have a look at the types of variables one by one. So we'll have a look at the continuous variable type and how it's visualized, and the concept of normal distribution, ranges. And then we'll have a look at the sampling distribution types, the other types, and the concepts of skewness and kurtosis. Then we'll see the nominal variable type and the concepts of odds versus probability. We'll also have a look at the data visualization, and that means basically we'll see how to visualize these different types of variables that we have discussed so far, and also the concept of multidimensional visualizations. And finally, we'll end it up by performing some correlations. So these last 2 points, all of them will be done in the SPSS, and this will be a practical exercise for you guys as well. So let's get started. Now, so these are different data types that we are looking at. What I normally like to do is that I divide the data types into two major categories. There are continuous or numerical types of data, and then there are categorical ones. Now, what I would like you guys to do is to focus on to the right side where there are examples. I hope that's going to make things easier. Now, in the numerical form, there are further 3 subdivisions. There are interval scale, then there are ratio scales, and there are counts. Now, interval scale basically in simple means that the numbers can be in the negative, they can be in the positives, they can be in fractions as well, as you can see here, minus 2.5. And the 0 is also included in the whole set of numbers. Now, the best example to understand would be of temperature. Say, for example, if an object has got a temperature of 35 degrees centigrade. Now, one of the interesting properties to make sense of this type of data is that this data is normally additive in nature. Now, that means that if an object has got a temperature of 35 degrees centigrade, and if the other object has got a temperature of 70 degrees centigrade, you cannot assume or say that the object B, which has 70, is having a temperature which is twice the first one. So all that kind of data in which basically what matters is the difference between the first and the second value, this is called as the interval scale. Now, the other type is the ratio scale. Now, that means basically, and if we look at the examples, it's mostly in the positive. It's in fact in the positive, and it can be in the fractions as well. Now, the important property is that it is multiplicative, and that means that if we have got, say for example, income of someone. So say if a person has got an income of 10,000, the other person having an income of 20,000 would definitely have got double the income of the first one. And this data has got a definite starting point, that is 0. So a person cannot have a negative income. So a person can start with a 0 income, and then it will go up. The third type is the count. And they're pretty simple to understand. They're all integers, and they are all in the positive direction. The second big type is the categorical. Now, they are further divided into these subtypes. The ordinal one, which is the first one, basically is a type of data which is expressed in the form of different levels. And the example is of education levels. So a person can be uneducated, or he can be matriculate, or he can be bachelor's degree, a master's degree, or he can be a PhD as well. If we have got different levels of a given data, we're talking about ordinal scale. The next type is the nominal or multinomial types, basically. So they are basically the type of data in which there is no specific order that we are talking about, like in the ordinal ones, and they are mostly expressed in the form of characters. Now, the best example would be names. So the names of the people, the different colors, the different types of examples of nominal. As we'll go into the exercises, you'll get to understand them better. The next one is the binary, and the important concept to understand is binary versus binomial. So binary type is basically a yes or no kind of a data, as we can see in the examples. So either it's a yes or it's a no. Either someone is male or female. The other thing is the binomial one. Now, binomial means that you have to pick one of those two options. Say, for example, if we pick yes. Now, binomial means how many times we get to see yes out of the total number of times that we get to choose anything. So, for example, if there are 10 options, and out of those 10 we have yeses 6 times, so the binomial representation will be 6 out of 10. So I hope so that makes sense of the different types of data, but we'll get to see their examples live as well. So let's go on to the next slide. Now, there is another way to classify the data types, and this is basically what normally we do as data scientists, and this is how we see the data whenever we are working with them. The second classification is basically to divide data into two big types. The first one is the dependent or the outcome, and the other class is the independent or the exposure or predictive variables. Now, there are different names that it's called by. It's the independent variables, the exposure, predictor, the features. So you'll get to hear one or the other, but in essence, everything is the same. All of it means the same. Now, so let's understand the dependent ones. Now, this is the data which depends on all the variables in the second box. So let's see it with an example. So if there is price of a property, now we want to predict the price of a given property. So this will be the outcome variable that we are interested in. Now, what determines the price of a property? So there are several things like location of that property, the size of the property, what is the crime rate in the neighborhood, and what are the number of parks and the schools, and a lot of other factors as well. So all of this actually helps us determine what will be the actual price of the property. If all of these variables go into the positive direction, we might have a high priced property as well in the end. So this is basically the other way to classify the data. Now, moving on to the next slide. This is a basic introduction to mean, median, and mode. I'm sure most of you would have had some kind of exposure to these three different measures of central tendency. So let's quickly have a look at the different definitions here. Mean is simply an average of all the numbers. So if, for example, we've got a set of numbers, like if you can see on the left side, from 0 to 100, if we add all of these numbers and divide them by the total number of evens, or the total numbers, then we'll get the mean. Median is the middle number. So if we arrange the numbers in an ascending or a descending order, like in this example from 0 to 100, then we can get the median by finding the centralmost number. And mode is the most fashionable number. Actually, mode comes from model, so that actually means the most fashionable or the most common number. So, and range is basically the range of all the numbers from the beginning till the end. So let's understand that on this graph on the left side. So now I'll start with the mode because that's the most easiest to understand. So if, say for example, we've got numbers from 0 to 100 arranged in this order. Now, by the way, this is the probability distribution graph or the frequency distribution. On the x-axis, you get the numbers that that you want to represent, and on the y-axis, you get the number of times that number actually is present in that given data set. So now we'll start with the mode. So in this example, as we can see, 30 becomes the mode. Now that means that this number 30 comes most of the times in the whole given data set. So it's the most fashionable, it's the most common number in this data set. Now the second number, the second thing to understand would be the median. In this example, this is 40, but if you have got a set of numbers and if you arrange them in an ascending or a descending order, the middlemost number would be the median. And if you don't have a middlemost number, like in case of even number sets, then it would be the average of the central two numbers. Now, mean basically is, as we've already discussed, this is the average. So in this graph, as we can see, most of the numbers are lying under 50. And there are some numbers which are lying more than 50 as well, and since they are not that common, so they can easily called the outliers. Now, if we add all of them together, since we are not just talking about the most common numbers, we are also talking about the ones which are not that common. If we add them all to each other and then divide by the total number of numbers, actually, then we'll come up with a number which is the mean. And it should ideally be somewhere in the center of such a graph. Now this distribution we'll discuss it, that this is basically skewed to the right. This distribution shows mean to be in the center, mode to be onto the leftmost side, and median is always in between these two numbers. Now, if we move on to the next slide, now what you are seeing is basically a Gaussian graph. So this is basically, we call it in the simpler terms, the normal distribution. Why is it called normal distribution? Because it's symmetrical, number one. And the other important characteristic is that the median, mean, and mode, all of them are lying in the center. So if we've got this set of numbers from -4 to +4, and if we draw the normal curve on this one, then we'll be able to see that all the numbers, when we add them up, we find out a mean, it will come out to be 0, the mode, median, all of them will come out to be 0. So that's the other property about this graph. So let's move on to the next slide. The other way to represent a continuous variable, so by the way, up till now we were actually representing the continuous variables, and we're having a look at these different measures of central tendency and the spread for the continuous variables. One of the other ways to visualize a continuous variable is to draw this box plot. To make it simple, basically it consists of central box, and then there are whiskers, which are essentially the tails on both the sides. Now, all of these numbers that we're talking in the earlier slides, for example, from 0 to 100, can be displayed in the form of a box plot. So what does everything mean here? Now, I'd like you to consider, and in fact to start with this box. Now this box has got 3 important points. There's a central line, and then there are 2 edges of the boxes. The central line is the median, as we saw in the probability distribution graph as well. And the edges are the percentiles, or basically the quartiles. Now, the first quartile, which is the 25th percentile, so keeping it simple, if you have got 100 numbers, the first 25 will be called as the first quartile, which is basically the first 25 percentile. The middle one basically is the median, and the 75th number will be called as the 75th percentile, or basically the third quartile. And by the way, the middle line or the middle number would have been called the second quartile as well. And quartile has come up from quart, which is basically the fourth. So it's basically the fourth division of a given data set. Now, and what is an interquartile range? It's basically the range between the 25th and the 75th percentile. So essentially, everything which is in between here in this box. So what are these whiskers? So these are basically the extensions of the data, and basically um, if you're talking about the positive whiskers, then this means essentially 1.5 times the interquartile range. So if this is the interquartile range, and if you multiply that by 1.5, any data which lies here in this range will be lying within 1.5 times the interquartile range, and any data which is lying above that will be lying beyond that range. So these are basically used to give us an idea about the distribution of the data, and also the fact that if the data has got any outliers or not. So as you can see here, there are two dots which are lying outside these bounds. So this would mean that there are two data points which are lying outside the upper bound, which is by itself 1.5 times the whole interquartile range. And in the similar way, we can have the outliers lying in the lower region as well. So we'll make these graphs ourselves, and we'll try to make sense in the upcoming slides. Now, the concept about standard deviation and confidence intervals. Now, to make it simple, so we have the same, our favorite probability distribution or frequency distribution graph, and this is the normal normal distribution curve, or the Gaussian curve. Now let's simplify the concept of the confidence intervals and the standard deviations. Now say, for example, if I give you a set of these values A, B, and C, and they're in the positive, and B and C can be in the negative as well. So for example, if you've got these 5 values, and if I ask you that out of all of these 5, I pick a random number, and if I ask you what would that number be, what would be your best bet? Well, I would assume that you would bet and you would go for A, because you would think, given this graph, there is a very high probability and chance that out of these 5 numbers, I would have given you A. This is basically, in simpler terms, this is the confidence that you have in A. So the more A lies, or the more a value lies in the center of this distribution, the more confidence you have in that number. Or the more it is closer to the center, the more confident you are. Now for the standard deviation, we have got a formula, and for the formula geeks, it would have made more sense for me to put that in, but I deliberately kept it simple. So just to put it simple, it's basically telling you about the dispersion of the data from the center. Now, since we have understood about the basic concept of confidence and the fact that there is something which is called a standard deviation, now on this graph, if we put both of these concepts to work, now that means, say, if for example the center is A, now from A to B there is a given distance. Now this distance, if we consider it to be one standard deviation, then, and if we are considering it on the both sides, so it would be from A to B and from A to minus B as well. So if we consider it to be one standard deviation on each side, the confidence that we would achieve by doing that for a given number to lie in this range will be about 68%, 68.3 to be accurate. Now that means that if I give you a number, you will be confident that that number will lie in this given range 68.3% times out of the whole 100. In the same way, if we extend the confidence interval from 1 to 2 plus minus, that means now we are talking from A to C and A to minus C, then the confidence basically increases to 95%, and the same applies when we are doing it with 3, so it becomes about 99.7%. So let's move on to the next slide. Now what we actually saw here in the earlier slide is basically a normal distribution curve, or normal probability distribution graph. Now, there are different kinds of distributions, and it's just to give you a glimpse, but what you would come across mostly is the normal distribution, the Gaussian one here. You may come across the uniform distribution up here. So, and there are some other ones which are important to at least understand. There are some exponential ones, the Poisson distribution, and the binomial ones as well. But for most of your practical purposes, you won't be having to deal with them. Some basic concepts about skewness and kurtosis. So if you've got a distribution curve for a given data, let's start with the skewness first. So now, say if you've got a data which looks like the first curve up here on the top. Now there is a tail on the right side, and there is more of a data on the left side. Now, naturally, the skewness, whether it's positive or negative, is determined by the tail. And since the tail is lying more towards the positive end of the data spectrum, then this skewness will be called as being positively skewed. And on the other side, if we've got the tail of the distribution lying onto the left side, which is mostly towards the negative side of the data spectrum, then this skewness will be called as being negatively skewed. The important thing to understand is that we normally classify the skewness as being whether the data is mildly skewed, moderately, or is it severely skewed or not. Now, mild skewness means, now this is basically a skewness statistic that we'll calculate very soon here in this lecture, in this SPSS. But if you get the statistic number to lie between minus 0.5 to plus 0.5, then we are talking about the data being mildly skewed only, or basically the other way to call it is the data is approximately normal. If the number lies from -1 to +1, then we are talking about a moderate skewness. But if it is if the number lies more than +1 and less than -1, then we are talking about highly skewed data. Now, the other thing is kurtosis. Kurtosis is basically the peakedness of a curve, how peaked it is, or how pointy it is. So leptokurtic, as we can see, is the most pointy distribution of a given data, and then there is a case statistic that we calculate for that. So if it is more than 0, then that means that the distribution is leptokurtic. The normal or the mesokurtic curve is basically it normally has got a case statistic, in this case of 0, and then we have got a platykurtic, which is mostly a flatter curve, and in this case the k value is less than 0. Now, moving to the next concept to understand. So the next slide is about the concepts of odds versus probability. So let's start with probability first. Now, probability is defined as this equation here, but let's understand it on dices here on the left side. Now, a dice has got 6 sides. Now, say if we want to calculate the probability of getting 3 whenever we throw the dice. Now, it might as well be 6, or it might as well be 5. So since there are 6 sides, the probability of getting 3 will be 1 out of 6. 3 is present 1 time, and the other ones will be present 5 times. So essentially adding all of that up, so it will come out to be 6. So essentially the probability of getting 3 will be 1 divided by 6. Now, what is odds? So once you've understood the probability, odds is really easy to understand. So odds is simply the event of interest, which is 1 in this case, divided by the not event of interest, so which is basically 5. So in this case, odds will be 1 out of 5. So we are basically not adding 1 plus 5 and trying to come up with a denominator which is 6 in this case. We're just mentioning the not event of this interests in this case. So I hope that clarifies the concept of probability versus odds. In probability, we add all the possible events in the denominator. In odds, we just mention the opposites of what we are expecting up in the denominator. Now, finally, on to some of the practical examples. And so what we'll be doing is basically we'll be visualizing a continuous variable. We'll be visualizing a categorical one as well. Then we'll be also visualizing two variables. So basically it will be a multidimensional visualization. And then while we'll be doing that, I'll be giving you some essential basic tips on the best visualizations to choose and how to go about it. And then we'll perform some basic simple descriptive statistics in SPSS. We'll make a cross-sectional table to get you started, and then we'll perform a simple correlation and try to interpret the results as well. So let's get started with the SPSS here. So let's have a look at the SPSS and do some practical examples. Now, I'm assuming that you guys should have some idea about SPSS, and you would have done some basic tests already, and if not tests, you should know about at least the data representation in this software. But if that's not the case, I would advise you to see some of the simpler explanatory videos on YouTube about SPSS, just to get you started on what is this, what does it look like, and what are these windows that I'm talking about. But assuming that you know some of the basics and something about the data types and how to set them in SPSS, I'll get started here. So what I'm doing here is I'm analyzing a data set which is a very popular data set in machine learning and data science. This is the Titanic data set, and tells us about the survivors in the Titanic ship after it sunk. There were some survivors who made it out, and these are this is the name of the name column for the survivors. Then this represents the class that the people were in, the first being the first class, and then second and third class as well, and the fact whether they survived or not, the gender of these survivors, the age, and then there are several other variables as well, whether they had a sibling or not, whether they were traveling with their parents, if they were children. There are some random value tickets as well, the fare which they had paid to get onto the ship, and some other variables as well. These are some of the two variables that I calculated, but I'll tell you how to do them eventually. Now, so this is the data set that we'll be dealing with. And if you go to the variable view, you would notice that I've made some minor changes. In the data type, I've converted the data variables into their respective types, and then I haven't made a lot of changes into these things. But I've also changed the measure. So this tells whether the data is nominal, as we've already explained, and scale here is basically used for continuous types of data. So let's get started with some basic analysis. I'll try to come back to this slide just to see what we are going to do next. So the first thing we'll do is to visualize a continuous variable. Now, how you draw a graph here in SPSS is by going to graph and then by going to the chart builder. So since I already have got an output here saved, what I'll do is that I'll close it, and then I'll get started with the rest of it. Now let's go to graphs, and let's go to the chart builder here. So once you open the chart builder, these two windows open. The first one is basically a simple the choice window, where you make certain choices about the type of charts that you're going to build. The second is the element properties, where you can tweak different parameters in a given chart. So let's start with the first type of chart, which is basically a continuous variable or a numerical variable. So what is the best type of chart which you would use to represent that data? So what I normally do is that I visualize it using the most simplest of representations, which is basically a histogram. So if I click on to this and drag and drop it here, so I get this empty uh, form of this histogram representation out here. And all I need to do is to go to a type of a continuous variable and drag and drop here onto the x-axis. So we'll be visualizing the age of these people. So let's bring it here. So once you drag and drop the age here, it gives you a rough estimation, but this is just an iconic representation. It's not the actual representation, so you can't trust that. Now, once we have selected, so this is one of the ways you can represent a continuous variable. The other way that I normally do it is by doing a line graph. So that's the other way that you can represent a continuous variable. And then there are probability distributions as well that you can do, but we'll just stick with these two main representations. The third most important way to represent this variable, continuous variable, is the box plot. So that would be the third one I went through all of them. So let's start with the histogram first, and let's press OK to get started. So this is how basically a histogram is represented. So we chose age, which is represented on the x-axis, and on the y-axis there is basically the frequency. So in essence, this is the frequency distribution plot as well, but it's not represented by a line, so it's called a histogram in this case. Now, so the important factors to remember about this distribution or the histogram is that you should be eyeing out or eyeballing the rough type of distribution and whether the distribution has got a skew or not, as we discussed earlier on, and the type of kurtosis as well, whether it's lepto or platykurtic or it's mesokurtic or basically the normal distributed form. So just eyeballing this graph, I can see it's slightly positively skewed onto the right side, and the kurtosis is not that bad, but it's pretty difficult to say here just by eyeballing. So we'll know how to find it in the numbers as well. But so that's the start. So this is how we represent using histograms this type of data. The other way to represent will be a line graph, but I would leave that for you as an exercise. Let's go to the next form, which is the categorical representation. So let's go and see how we do that. Let's go to the graphs, go to the chart builder. And now we are doing a categorical representation. There are two main ways that they are represented. What I don't want you to do is to go for this one, which is basically the pie chart. And why I say this is, for example, if you wanted really to do this, and the one that the one variable that we want to see, say for example, is sex. So let's put this variable here on the x-axis, and let's make a chart just to see. Now, is there any way? Now, why I don't like is this simple fact. Now, is there any way you can tell what percentage of this graph belongs to female and what percentage to male? I know you can give a rough estimation. You might say it is 70-30, you might say it's 60-40, but you can't be that sure. Plus, if it was a close call, you wouldn't have been able to even tell whether something is more than the other. Now, there is a way. If you can double click on this graph, and if you can go into this button which is show data labels, and if you can click on that, you can see it's 65-35 roughly. But again, it's mostly a guesswork if we didn't do this. So that's why I don't like this type of graphs, and especially they don't look that official as well when you are representing data to in front of someone else. So what I like normally is that I like to do the other form of representation, which is the bar plots. So if we drag and drop the bar plots, which I selected from here onto the left side, and if I choose the sex, it's already selected, but just for the sake of demonstration, if I do that and if I click OK, now we get bar plots. And in this form or in this representation, we can absolutely be sure that the males are, there are many more males in this graph as compared to females, and we're absolutely sure about that, since this is a side-by-side representation of data when compared to a pie chart. The other thing is that you can make rough estimations about the counts as well, and also the fact that males can be twice as more than the females, or the proportion of difference. So there are a lot of positives in this type of graph, and easier to understand as well. The next thing that we'll do is visualize over two dimensions. So what does that mean? So let's go to graphs and understand there in chart builders. So we are visualizing over two dimensions. So what I normally do is that I think in the x dimension and the y dimension. And what I normally do is that I put the categorical variables like sex and all of that onto the x dimension, and the ones that we are trying to evaluate, say for example the age, I normally put them onto the y dimension. So the next question, what is the most ideal, or one of the most ideal graphs to represent that kind of data representation? So what I normally do is that I straight away jump for a box plot because of several reasons. So I'll tell you why. So first, let's drag and drop this one. And onto the x dimension, as I told you, let's put in the categorical variables. And onto the y dimension, let's put in the age, which is one of the continuous variables. Now what I'm doing by doing this graph is that I'm producing a graph which is evaluating two dimensions, x and y, at the same time, and where one of the variables is a categorical one and the other one is a continuous one. So if we do it like this, and if we press OK, we come up with basically the box plots. Now, as I've already explained the concept of box plots, or sort of explained the introduction to it in one of the earlier slides, it contains a box in the center, and there are some whiskers, as I've already explained. Now, why is this representation better? Because number one, it tells us generally about the bulk of the data and where is it lying. Now that in this case, in this example, in case of females, the bulk of the data, or the middle 75% of the data, lies from 20 to 40 roughly. So it lies in this range, while among the males the range is a bit higher for the middle 75% of the data. So it also tells us about that. Secondly, it tells us about the median differences as well. So it looks like in males the median is slightly higher as compared to the females. The other importance is that it also tells us about the general skewness of the data as well. So as we can see here, that most of the data, since it's lying towards the lower end, which was basically the negative end when we are imagining a probability distribution. So if I can draw it for you, so say for example, if we are imagining, so let me just quickly draw it for you and let's make a sense out of it. So if we are imagining the same probability distribution, so there was a negative data and then there was a positive data. So this would be positive and this would be negative. So this negative one, it's not actually negative, but it's towards the negative end, and this is towards the positive end. So if we invert the whole thing onto that side, and if we convert this onto a box plot like this, then this negative will be this region and this positive will be this region up there. So let's go back to the slides here. So this is mostly that portion. Now if since the central data is mostly towards the negative one, and the skewness, or basically the rest of the data is towards the positive, it gives us an impression that it will be slightly positively skewed. And it's the same on this case, in case of males as well. Now, it's only a general estimation. The best way to visualize skewness or kurtosis would be definitely to go with a histogram, so as we already explained. Now, the other important thing that this graph tells us are the outliers, as we can see. So these numbers basically are is the data value, or the data entry in our data set. But in general, it tells us that there are about it seems like there are about 5 or 6 outliers which are lying beyond 1.5 interquartile range of this data set. So if that doesn't make sense, I suggest you to go back and see the earlier slides where I explained this fact. So let's go back to the graphs, since the video is becoming a bit too much in size. So the next thing to see here would be simple descriptive stats and making a cross-sectional table. So let's go back and let's make that table now. Now, some of the simple descriptive statistics, how I do mostly is that you go to Analyze and you go to Descriptive Statistics. Now, the 3 most commonest buttons that you will use for descriptive statistics will be Frequencies, Descriptives, and Explore. You can do most of the things by using frequency. You can do some interesting cross sections by going to Explore. So I mostly tend to use either the first one or the third one. So let's start with the first one, frequencies. Now, say we want to analyze a continuous variable. So we choose the age and we put it onto the right box by selecting this arrow. Now, if you go to the statistics here, the first button, you will be able to choose a lot of different things. So let's uncheck everything. So as we discussed, you can select mean, median, mode. We can also select quartiles, as we explained before. So this will give us the first, the second, and third quartile, which is 25th percentile, 50th, and 75th respectively. So we can select that as well. So let's do that quickly. We can also choose to get the standard deviation, the minimum and the maximum numbers. And let's say for this case, we want skewness and kurtosis as well. So let's click continue. And then if we go back down here and if we select the display frequency tables, now I wouldn't suggest it to be selected for age, because it's a continuous variable and it will give us a very long table. So I would turn it off, but we would do that for some of the categorical variables. You can select charts and you can do some other modifications, but let's keep it simple. Let's go with this one first. Now, so we get this table which tells us about the mean, median, mode, standard deviation, as you would expect. It also gives us a value for skewness and kurtosis. The skewness is about 0.3, which is in the positive direction. So it shows that there is some skewness in the positive direction, but it's not that much that we should be worried about. So if I can go back to that slide, and if I can tell you about the skewness and kurtosis. So this was the range. So since it's from minus 0.5 to plus 0.5, we are talking about mild skewness. The other thing was kurtosis. So here it comes out to be 0.7, I think it is. Yes, 0.17. Now let's go back to the range. So this is basically in the positive direction. So it seems like a leptokurtic curve, but it's not that leptokurtic. So if it's more than 0.5, and to be more accurate, if it's more than 1, then we should be really worried about kurtosis. But otherwise, in this range, this can be ignored. Now, the other thing that we'll do, so let's go to the next things. So this is again making simple descriptive statistic tables. Let's go back to descriptives. For the next thing, what we'll do is that we'll go to frequencies again, and this time let's select one of the categorical variables, and say we've selected sex. And since we don't need any of these, as we are dealing with a categorical variable, so we won't be needing any of these. And we'll have to select the frequency tables here because that's what we are interested in. If we select OK, we'll get a frequency table like this. Now, it tells us about the percentage and the actual number of males or females in the whole population set. And these are the frequencies. This is the percent. Valid percent actually excludes the missing values and tells about the rest of remaining values. Cumulative percentage is basically adding up the percentages. For example, if we add 35 with 64, we get 100, so it comes here. So, but mostly we are not concerned with these valid percents or cumulative percent. We are mostly interested with these first two values, because most of the times we would have taken care of the data to remove the missing values. So this is basically to get a simple descriptive table for a categorical variable. Now let's go back to the next thing. So let's make a cross-sectional table as well. If we go back to analyze and go back to descriptive statistics, then there is this option in the form of a cross tabs. Now I didn't tell you about explore, but let's in fact quickly go and see what we can do with explore as well. Now with explore, what we can do is that we can analyze two variables side by side. So say for example we want to analyze age by gender. Now that means that if you want to analyze age of males and age of females, so what we'll do is that we'll put the age in the dependent list, and we'll put the gender or any categorical variable for that matter into the factors list. So factors is basically the other name for categorical divisions of the data. And we can go to statistics and we can select different calculation values here, or we can make some graphs. In fact, let's make some graphs here. So let's make histograms, and let's factor levels together. So we can factor the levels together, or we can factor the dependence. That means that we can see the dependence, which is age, for example. So we can do these together, but just for the sake of simplicity, just ignore if it existed there. Let's select the normality plots, and I'll tell you what does that mean. So let's go to continue and let's click OK. It gives us these two tables. So the first one is the same frequency table as we more or less saw up here, but the important one is the second one. So this is the descriptive table. It tells us about the same things that we saw before, as you would have guessed by now: mean, median, variance, standard deviation, and all of that. And it tells us about the minimum, maximum range, and all of that, skewness and kurtosis. But it divides that by gender, and for the males and for females as well. And in the same way, it gives us some graphs: the histograms for males, the histogram for females. Right. So there. I'd like to explain these two interesting graphs for you. These two things. Number one is the QQ plot, which we normally see to estimate the normality or the normal distribution of the data, and the other thing is these two tests for normality. Now, what are these tests? You can either look on the first one, the Kolmogorov test, or you can look at the Shapiro-Wilk. It doesn't matter. I normally go for the Shapiro-Wilk because it has the tendency to handle the small sample sizes as well, and can go up to a sample size of 2000 as well. But for a smaller data set, I normally go for Shapiro-Wilk, or I go for a QQ plot because it's simpler to make and easier and visually interesting as well. Now, if we go to this Shapiro-Wilk, and what does this mean basically? Now, if I give you one simple answer to how to approach and what to make out of this. Now, what it says basically is that it's testing whether this distribution that we have, since it's from a sample and this sample is from a population, what Shapiro-Wilk tests is that whether this distribution is different from normal distribution or not. or basically in a more accurate terms, whether this distribution comes from a population which is normally distributed or not. Now, uh, we can't accurately say whether it comes from that population or not, but we can only reject or accept the null hypothesis. So what is the null hypothesis? The null hypothesis in this case will be that this distribution or this sample is coming from a parent population which is normally distributed. So so that is the null hypothesis. And what is the alternate hypothesis in this case is that it's coming from a population. It's in fact not coming from that normally distributed population. So it's coming from a different population, but it's not coming from the normally distributed population. Now, how to make sense of these significant levels or p-values? Now, if we have a p-value less than 0.05, now that's an arbitrary value that you can choose. You can set this value to be 0.05, or you can set it to be 0.01, but whatever you choose. Say, for example, if you choose 0.05, so that means that if it is less than 0.05, like it is in case of males, and it is, but it's not in case of females. Now, in case of males, it's less than 0.05. That means that this population is basically, it means that we fail to reject the null hypothesis. That means we fail to reject the fact that this distribution might have come from a normally distributed population. But let's put everything into a simpler one-line term. In one line, if it is less than 0.05, the population is not normally distributed. Now you can ask me that, Shoaib, I didn't have to go through this difficult test and this these extra few steps. I could simply see this graph and I could make that sense myself. I could say that, well, it's slightly positive curved, especially in males. As you can see, it's slightly positively skewed, not that much in females, as we can also prove in this test as well. So you could argue that, I can assume that by seeing and quickly eyeballing this graph. I agree to that fact. You can do that, and that's why histograms are amazing. But to prove that, and especially when you're applying a t-test and when you'll be doing a lot of those tests, then you would have to be sure that your population is normally distributed. And one of the ways to make it sure is to do a normality test, a test of normality, in fact. And this is to prove to obtain a solid proof that you are actually having a normally distributed data. So enough said on that. Quick word on QQ-plot. So what is a QQ-plot? It would be difficult to understand in the beginning, but it's basically the expected distribution of a given value. So basically they are the quantiles, the expected quantiles versus the observed quantiles. But to put it simple, to keep it everything simple, if you have a graph in which every dot is in a line, that sample is normally distributed. But if the dots are swaying away, then the sample is not normally distributed, to put it simple. If you have a graph where the dots are making a curve onto the upper side, the sample is positively skewed. And if they are making a curve onto the lower side, the sample is negatively skewed. So just to put it simple, but there are different permutations. If there are lines onto the positive side and then there are lines onto the negative and there is a gap, then the sample is basically having a binomial distribution. That means there are two different distributions. But enough said. So let's move on to the next thing, which is basically performing a simple correlation. So let's do that. So let's go to analyze to perform a correlation, and let's go to correlate, and let's go to bivariate. Now, so how to do a simple correlation? Since the correlation is between two continuous variables, we have to choose two continuous ones. So let's choose age and fair. Now, by doing this, we are checking whether a person's age is related to its fare. That means the older a person, the more he pays. So is it related or not? So let's test that theory. Let's go to options. Well, we don't have a lot to do here. Uh, so let's, among the other settings, let's select Pearson's. So there are basically two types of correlations that we perform, the Pearson's one and the Spearman. If the sample is normally distributed, you go for Pearson. If it's not normally distributed, you go for Spearman. Spearman is a bit more conservative test, difficult to give you a significance there. But let's select Pearson because our sample is more or less normally distributed. And yeah, and we're selecting two-tailed because we are testing for a positive and negative correlation as well. So let's select OK, and you will get a table like this. So you only have to see either the first section or the second. It doesn't matter whatever that you see because the numbers are repeating. So for example, if you're testing for age being correlated with fare, now age in this row and age in this column are perfectly correlated, and it makes sense. So the correlation basically is telling us whether a data is related to the other data or not. So let's quickly go to an example to see. So for example, if we have got a data on x-axis, a variable, and a continuous variable on the y-axis, if the data or the data points, they converge onto each other so that any increase in the x value causes an increase in the y value, then we get a strongly positive correlation. If there is a decrease, that means any increase in the x causes a decrease in the y, then there is a strong negative correlation. But if the data is not as compactly packed as in these initial curves, for example, as in case of the central curve, then the data is still positively correlated, but it is weakly positive in correlation. And if the data is randomly spread and it's not correlated, and then it's not correlated, so the correlation will be negative. So let's see it here in this table. Now in this table, age seems and it's showing some positive correlation with fare. The value is 0.09. Now since the value is not 1, it is not perfectly correlated, and since the value is not 0, it doesn't mean that it means that they are somehow correlated, and since the value is between 0 and 1, so there is this, it means that this is a positive correlation. But how much is the other factor? Now this is 0.09, even less than 0.1. This is absolutely a very weak positive correlation. But if it was more than 0.5, then we were talking about, then we would have been talking about a moderate correlation. And if it was more than 0.7, then we could have been talking about a positive, strong correlation. So this is one of the ways to look. The other important thing in this table to notice is the p is the level of significance, basically, or the p-value, which here comes out to be 0.01, which is less than 0.05, which means that this finding that you have obtained up here, the positive correlation, can be by chance only in 0.01, which is 1% of the cases. That means 99% of the times you will actually get this type of a correlation whenever you would compare these two data types together. Now, basically, in one word, so what is the interpretation? What is the sum of everything that we have said? The essence. The essence is that there is some correlation which is positive and which is statistically significant as well, but it's a very mild correlation, so much so that we won't even be considering it for any further testing. So that is pretty much it for this video, this lesson. I hope so that I didn't bore you with it. I know it's one of the most boring things to do when you are new to statistics, and when especially you don't have any experience in that. The other disclaimer that I want to put in here is that this video series is specifically aimed towards the beginners, especially the clinicians and the practitioners who are new to the field of data and statistics, or who haven't had a lot of time experimenting with it. So I'm not talking to the experts here, with due apologies. And if you feel that I've made it too simplified, then you can give me a feedback on that, and then I would definitely improve on that. But the idea was to give you the practical points that you would take with you, and then you would apply in your tests, rather than going to the extreme details and formula of everything. Before closing up the video, again, thank you so much again for listening to the whole video, this long lecture of a thing. And if you've got any questions, I'm more than happy to answer them in on my website, and you can ask them in the comment section of this video, or you can ask them on the Facebook group that I've made. You can find me on this website, where you will find the data set that I've used in this exercise, and you can find it there, and you can apply your test yourself if you've got SPSS. If you don't have that, don't worry about that. We'll get to the R understanding or practical understanding of the R language in the next module, and R is free, so everyone can use that. Thank you so much again for joining me in. This is Dr. Shoaib signing off. Ciao for now.